We can also use these behavior over time graphs to just interpret the general process of any given system. In this case, you can click on the graph and see, okay, well, 2 ATP were produced here, and then 2 more ATP were produced here, and then, ooh, a whole bunch of ATP were produced here. And so we can start picking out, well, which part of cellular respiration is happening at which stage. And if we were to look at a model, we see, well, 2 ATP are made during glycolysis, 2 more during the citric acid cycle, and then a bunch more is made on the electron transport chain by ATP synthase. So one thing is I'll have students have a behavior over time graph and plot out the initial conditions. From there, then I will perturb the model in some way and have them predict those effects. So by disrupting the system, how is that going to affect the dynamic behavior of the model? One of my favorite parts of this simulation is helping students understand the power of the proton motive force, or chemiosmosis. So what happens generally is NADH is used to carry electrons along this electron transport chain, which then is used to start pumping hydrogen ions into this intermembrane space. So we start pumping all these hydrogen ions into this intermembrane space. And as we pump hydrogen ions into this intermembrane space, those hydrogen ions are used, they flow down their concentration gradient through ATP synthase, and in that process, that free energy transfer of the high concentration of protons or hydrogen ions here is used to phosphorylate ADP to make ATP. Okay, so once students have an understanding of that, we can then go to the model and see what kind of misconceptions do they have and what kind of predictions are they going to make. So now, if I limit glucose all the way to 0, I'll ask students, what do you predict will happen with 0 glucose? And a lot of them will say, well, nothing will happen because there's no fuel source. So we run the simulation and we see that's right, no ATP is produced. So good news, and we can have them graph that. That right here, 0 glucose. Then we can say, okay, and that is at a pH of 7. So now let's do that again, but adjust the pH to 8 and have them predict it, and then we run the simulation and same thing. So very similar results here where we get 0 glucose, pH of 8. Then we adjust it to a pH of 6, have them predict that. And we run it and we get this surprising result, right? And then we have them go back to this model and say, okay, well, why is that? And this is where a lot of misconceptions happen. One of the most common ones is, well, do students understand that an increase in protons is a decrease in pH? Let's get through that misconception first. Well, once they understand that, they'll see, okay, well, in our intermembrane space here, our pH went down, so there's more hydrogen ions here than anywhere else. And because of that, we've already created this concentration gradient. So this is what's needed to drive this ATP synthase is just an increase in hydrogen ion concentration. So then students will graph this and we'll look at the scale here. Well, this is going all the way up to 77 ATP. Certainly not realistic, but it's going to go way off the charts, right? And this is 0 glucose, but a pH of 6. Now students can use this behavior over time graph to help explain differences between different disruptions in the system. After we disrupt the system and we create these behavior over time graphs, then I like to have them connect it back to the concrete model. So in this concrete model, we have NADH, which is driving this proton gradient, which then that proton gradient is used to drive the production of ATP. So why did this happen with these different disruptions? So one thing I'll have them do is they have this recorded on a whiteboard, and then on a whiteboard or paper, I'll have them do something like this, where, okay, here is ATP synthase, and under these different conditions, now use your behavior over time graphs of ATP over time to tell me the story of what's going to be happening along this mitochondrial membrane, inner mitochondrial membrane. So at initial conditions, they might do something like this, where protons are being pumped out using electrons, those high energy electrons from NADH, and then they end up flowing back in down their concentration gradient to produce ATP. Here, what's happening is without glucose, there's no pumping of protons, so the protons should be equal on either side and no ATP is being made. Lastly, though, when the pH is low, there's a much higher concentration of protons here, and so those protons diffuse down the concentration gradient and ATP is made. And so now we are connecting back a behavior over time graph with a bunch of concrete models and disrupting the system. This connection of concrete models and the computational models really helps students try to understand some of the dynamic behaviors and helps them to try to understand what's happening in this given computational model and simulation, so then they can start running their own experiments. Behavior over time graphs are really important for systems thinking and really help students thinking of behaviors of not just being strictly linear like this, but have different non-linear dynamic behaviors. In this video, I wanted to show you that behavior over time graphs can generate discussion for quantitative behavior of a system. Also, you can engage learning by having students actually predict the outcome without actually knowing everything that they need to answer the questions. That's that pretest effect. Third, they can understand the boundary of the system. So what is this simulation actually testing? What is the boundary of the model? Do that by, you can compare different timescales students might have in their mental models and then how they think the variables are going to respond. And that helps them calibrate towards the simulation that they're going to be using. Also, once you run the simulation, you can validate their predictions. So they made a prediction, then you can run the simulation and validate their predictions against the simulation's results. And lastly, you can use different concrete models to have students draw and compare what's happening under different parameters. So when you manipulate a variable in one way or another way, you can then graph that result, but you can also draw different behaviors like this. And so students can see what's happening in the actual system itself. So I hope you use behavior over time graphs, and I have a whole host on my website. If you'd like to be a Patreon patron, you can subscribe. Thanks. And they